All right, we are going to begin our chapter 4. Finally, took us too long. All right, so we're going to start off chapter 4 with a couple of things we already know, but then we're going to extend it into our calculus knowledge. Some of this actually we've kind of discussed a little bit as we've gone. All right, so moving forward here, we're going to look at just the idea of absolute extreme values, something we know a lot about already in all of our studies of functions and that sort of stuff. So we're going to say let f be a function with a domain D, whatever the domain is, doesn't really matter. And then f of c is the absolute maximum on the domain if and only if that f of c is bigger than all f of x in the domain. Now we know this from our quadratics being like a negative quadratic. We have an absolute maximum at the vertex because there's no other point bigger than it. And likewise, f of c is an absolute minimum if f of c is less than all other points on the domain itself, on the function. All right, so these are kind of things that we already know, and we're going to use them in a little bit. This absolute extreme value thing, this is very important to us. It actually moves right into this the extreme value theorem. And this is if f is continuous on a closed interval a to b, then f has both a maximum value and a minimum value on that interval. It's guaranteed. There's no way about it. If f is continuous on a closed interval, then f has both a maximum and a minimum. And something along that line of, let's just say we had something a little bit like this. Kind of looks like a sine curve. If we had this out here as A and this endpoint as B, and it's defined on the closed interval from A to B, so these are closed points at the end, and we know this graph to be continuous, we can see here, this right here at the top is an absolute maximum, and we would say that's on the interior point of the domain, because it's in between A and B. And then likewise, we could have an absolute max or minimum right here. And again, that would be on the interior. But we can also have things on the endpoints as well, guaranteed because we use the values of A and B. So if I extended this thing down a little bit farther, and it went down here, now we have something that almost looks like a cubic. And said, actually, A starts way over here. Now you notice we have an absolute minimum that's on the end point of the domain. And that's completely legal, and that's one of the things that our extreme value theorem guarantees us. There will be an absolute max and an absolute min somewhere on this domain, either on the interior between the 2 points or at the endpoints themselves. All right, just as we always learned with when we started with quadratics, we went to polynomials and dealt with local extreme values. If C is an interior point, so now we're dealing with interior points of the domain of the function f, then f of C is a local maximum if and only if f of C is greater than all f of x's on some open interval containing C. And you can kind of think about your understanding of polynomials and local min, local max, that sort of idea. And we have our local min definition here. If f of c is less than all f of x's on some open interval containing C. Now bear with me. I mean, we're getting to the calculus piece in just a second, but we're just kind of redefining our understanding here. Okay, we have a local extreme value theorem, actually. If a function f has a local maximum value or a local minimum value at an interior point C on its domain, and if f prime exists, so now we've connected to our calculus, then f prime at c equals 0. And this is actually something we've kind of done a little bit. If we took the derivative at a point and found that the derivative was 0, then we knew it was a horizontal tangent, stuff we've talked about earlier. And that's really what we want to get at today, is kind of taking derivatives and finding absolute max, absolute min, local min, local max. That's really what we're kind of focusing on today. All right, so we have this big idea of critical points. There's lots of different types of points, but critical points are points on a point on the interior of the domain of a function f at which f prime equals 0 or f prime doesn't exist. These are called our critical points. That's just our definition. It's the word we're going to use for those particular things. So we can have a critical point at some value that makes the derivative 0, or at some value that makes the derivative undefined. And the first one here is we're going to look to find extreme values of the function f of x equals x to the 2/3 power. And we're looking at the interval from -2 to 3 inclusive. So because extreme values can occur at endpoints, you need to find the value at the endpoints as well. So hopefully I can read everything okay here. We're going to look at f of -2, and we hope that, or we not hope, we just want to see what the value is here, because we want to see if eventually this is going to be a local min or local max. And f of -2 is, oh, what is that? -2 to the second power is 4, so we have the cube root of 4. Lovely handwriting on the mouse. And then we also want to do the other endpoint, f of 3. And f of 3, same thing. If you guys having troubles with this, this is just 3 to the second power and then the cube root. And that's how I did it just a second ago as well. So it's the cube root of 9. And we can get some approximations of those in a minute if we need to. But hopefully you know that cube root of 9 is bigger than the cube root of 4. I hope you know that. Okay, so those are the endpoint values, and they may or may not be critical points. They may or may not be. We don't know yet until we figure out the derivative. Okay, so the derivative of this, the function itself, so f prime at x is, let's see, I think we know how to do this, 2/3, and it would end up being x to the -1/3, so I'm going to put it down here as the cube root of x. So I look at this point, I look at this function, and I go, well, this function doesn't have any zeros. So there's no f prime at c that makes a 0 here. But there is a point at which this makes it undefined. So we know that if I plug in a 0 here for x, this makes this fraction undefined. So that means f of 0 is a critical point. This is a critical point, and these might be critical points. So let's go back and let's plug in f of 0. Well, f of 0 is, let's see, what is that? F of 0 is 0 to the 2/3 power. Well, that's 0. Oh, and then I wrote 2. I don't know what I'm doing here. I'm bad as on this and as I am on the board. So f of 0 is 0. That's better. Well, now I want to figure out what are those, what are the extreme values here? Which one's the minimum? Which one's the maximum? And it's hard to ask you the question here, but are we guaranteed a minimum and a maximum? And I hope you're saying yes, because I just told you could, because the extreme value theorem says a function defined on a closed interval will both have a maximum and a minimum. And you'll notice here, 0 is the minimum. Lovely handwriting. 0 is the minimum because it's smaller than cube root of 4 and smaller than the cube root of 9. And you'll actually even kind of notice that cube root of 4, I hope you know this, is probably smaller than the cube root of 9. And that means the cube root of 9 is the biggest number. And that tells me this is my maximum point. And you can graph this and determine this for yourself, that that's actually the minimum and the maximum point. All right, so I'm going to erase this here, and I'm going to look at our next example. Our next example is g of x equals 4 minus x squared to the negative 1/2 power. So this is really 1 over the square root of 4 minus x squared. Now, one of the things that you have to remember is the domain of this function. The domain of this function is not a closed interval. This domain, if you are kind of follow along here, this is 1 over the square root of something. And everything under the square root has to be greater than or equal to 0. But I can't be equal to 0 because it's in the denominator. And those 2 points at the endpoints are -2 and 2. That's what makes this thing 0, and that's really what I was looking at, right? So my domain is -2 to 2. So I need to figure out, well, those -2 and 2, I can't use them, right? So I can't plug those in to see if they're critical values because they don't even exist. They're not on the domain of the original function. So what I need to do then is actually find the derivative. Well, I kind of like writing it like this because I don't have to use the quotient rule. I can just use the chain rule and the product rule, and the product rule, not the product rule, power rule. Okay, so the power rule says -1/2 out front. I'm just going to make a big fraction bar because I think there's other stuff going on. Times -3/2 of this thing to the power of -3/2. So 4 minus x squared to the 3/2 power, and then times the derivative of the inside piece, which is -2x. And a few things are going to cancel here, like the -2 goes away. And this is kind of nice with my eraser here, right? So the 2 goes away with this 2. The negative goes away with this negative, and I'm just left with x over 4 minus x squared to the 3/2 power. And so I need to figure out which ones of these are critical points, or what x value will give me some critical points, and what x value is going to give me some undefined points, that sort of thing. So you'll notice in the numerator tells me that if I plug in x equals 0, I get a 0. That means, hey, where's my mouse? There we go. So f prime at 0 equals 0. And that's actually what I want, right? So that's a critical point. F prime of 0 equals 0. And I can think about the denominator as well to think where it's undefined, but that's at 2 and -2 again, but I can't use them because they're not in the original domain. So f prime at 0 is my only critical point that I have. And if you've graphed this already, you'll have figured that out already. So I want to go back to the original function. I want to plug in 0. And if I plug in 0, oh, sorry, this is function g, isn't it? It's g at 0, g prime at 0. Let's change that. Okay, so g at 0 is, let's see, 1 over, remember, because that's the negative exponent, so it's 1 over 4 minus 0. Well, that's nice. It's 4, and it's a square root. So the square root of 4 is 2, And you'll notice that the point, this is a point now, so those of you guys that aren't really listening to me, this is not a point, this is the domain. This is the point 0, 1/2 is the minimum point on the function g of x. And again, you can verify this graphically. You can verify this with other points if you really want to. And actually, I didn't even tell you. You have no idea. You had no idea that this was a minimum point, did you? You could test some points that were really close to 0. Like if you plugged in a 1, or actually not a 1, a 0.1, 0.1 on both sides, you would actually notice that they're bigger than 1/2. And because they're bigger on both sides of the 0, you would have known that this was a minimum value. But if you would have graphed it already, you would have seen that this is obviously a minimum point. All right? So moving forward, you'll see that I'm done already. So this is kind of a short-ish assignment. There's a lot of derivatives that you're going to be needing to find. You're really going to be needing to find the critical values, any minimums and maximums you might have. And right, so let's have a little fun with this. You can do whatever you need for the assignment itself. And I will see you guys Monday with any questions. We'll work through this. And I hope you guys have a good evening, and see you guys tomorrow.